Welcome to a Climate Conversation podcast. We are so excited about what we'll be talking about today. This is a complement to the documentary A Climate Conversation, which you can watch for free at climateconversation.com. A Climate Conversation documentary is the vision and project of executive producer Walt Johnson. Walt is a geophysicist. He's been a geophysicist for over 50 years, and he just wanted to have a conversation to talk about this issue that we hear about all the time. Walt Johnson, welcome to the podcast.
Thank you very much, Kim. Thank you.
And our guest is James Camus, and I'm going to learn something about plate tectonics and continental drift. And our spokesperson, Dave O'Rourke. Dave, welcome. And you're going to set this up for us because we're guaranteed to learn something today.
Thanks a lot, Kim. Welcome, James. It's great to have you here, Walt. Always great to see you. Thank you for joining us for this. There's an old saying in Hollywood, now for something completely different. And that's what this podcast will be today. We've been very fortunate to have who's who in support of our film and in the production of this podcast. I want to encourage listeners and watchers to go and browse through climateconversation.com and look at some of the podcasts we've had, and you'll be introduced to a wide variety of people who bring realism and who bring an adult and scientific approach to this topic, which captures so much of the political, social, and cultural energy of our country and all the way around the world, and is the subject of an incredibly important and potentially staggeringly expensive set of proposed solutions. But you will not have heard anything in any of those podcasts or any of the dialogue about what that's similar to what you're going to hear today, which is a very plausible alternative explanation for the principal causes, and perhaps in some cases, the cause of changes in our climate. We have an absolute expert in this area here, James Camus, who has a career in geology, has a bachelor of in geology from Northern Illinois and a master's in geology from Idaho State, which I believe is in Pocatello, Idaho, if I'm not mistaken. Mm-hmm. I've got a son who lives in Idaho Falls. We want to welcome you. We want to celebrate your 40 years helping human flourishing by the finding of and the development and exploration and delivery of energy, not only to the American people, but to people around the world. There is no human flourishing without energy. There is a huge conversation, and we are part of it today, about how we can adapt to changes in the climate. How can we understand them better? What are the causes of these changes? What are some potential changes that could occur? And in the context of this conversation, how can we understand the problem better so we can engage in cost-benefit conversations about the right way moving forward? So can you give us your origin story? Tell us, we're fascinated. We know a little bit about your background already, but I'd love for you to share with the listeners how you got here, what it is that fascinates you about this topic of plate climatology.
Well, it started in 1977 as finishing up my graduate work. I saw two events that really changed my mind, opened up my mind, I'll say. So the first thing was I had finished a course in plate climatonics, continental drift, and that was just fascinating to me. I didn't know anything about it prior. The continents move together and come apart. And the next thing was scientists admitted that they didn't know much about our ocean floors. And they supposed or thought that the ocean floor didn't have many creatures, or there wasn't much going on. It was just this mud, flat plain. So they put together some money and they started a project to get a submarine built that withstands the pressure down there, called the Alvin submarine, and they were going to put it all the way down to the bottom of an ocean in a deep area. So they did that. It was off the Galapagos Islands, which is a very volcanic area, and there's a deep basin there. So they dove down, and what they saw was absolutely amazing. They went below the photic zone, the light zone, down into the dark zone. They got to the bottom. When they turned on their lights, they were astounded. They found all sorts of life and unusual creatures they had never seen before. And they were all going around this big geyser, kind of like Yellowstone, but it was on the ocean floor. And it emitted lots of chemicals, they found out later, heat. And the animals were surviving off these chemicals. So those two things to me just opened up my mind. And I thought, there's more going on with the geology in the oceans than ever before. And through the years, since 1977, I've studied this and all sorts of different research studies, different scientific disciplines. So that's how I got started at it.
Well, it's fascinating, I think, to anyone when they first learn about it. I have a memory of when I learned that the Earth is made of these plates that move around pretty quickly. Got past me. I was a business student, not a geologist. So, but you look at these simulations of how the world has moved around and everything, and you start thinking, how much energy does it take to move Africa? Seems like it would take a pretty large motor to move something, that weighs the Earth. And yet this is the nature of our planet. Now, I know Walt is a geophysicist. He knows quite a little bit about this, and a huge amount more than me. And I know that Walt can help guide us through a little conversation about what plate tectonics is in conversation with you. And I think we have some slides here, Walt.
Yes, thank you. Thank you very much for setting this up. Since a lot of people don't know about plate tectonics, I thought I would start it out and give a little background on it. Plate tectonics, I was talking to a colleague. He graduated with his master's degree in geology, went into the Air Force and was in Vietnam. And but when he went, plate tectonics was not even a hypothesis. When he got back, it became a hypothesis, a theory, and a known fact. I mean, all of this happened rather suddenly. And we got a few slides to set this up to show you where the planets were at different times. And what you're looking at now is the planet as it is today. And if we go on to the next slide, if we would please. Okay, there is the planet during the ice ages. And you see not a lot of movement. It's a little bit colder, and that's okay. And then the next slide will be important. And here is where the planet was at the Cretaceous time. So notice some things here about it. Notice on the western half of the U.S. continent, the North American continent, you see what's called the Cretaceous Interior Seaway. It does have a big role in climate in us, because this is why some people say that United States and Canada are really the Saudi Arabia of natural gas. The sea was a very shallow sea. It was a stinky sea, and it had lots of algae growing in it. And so a lot of things dissolved and decomposed and went into natural gas. Also, look down at South America and Africa at the lower part, and they're a little bit closer together, and people had hypothesized for some time, isn't it strange the two are so similar in shape? So then our next slide, if we go on, this is the last one I'll show like this. This is what it was like during the Cretaceous time. Here, Africa and South America are put together. I had the opportunity to work a lot in Africa and South America. And the rocks at that time, if you look at them in one place and look at them at the other, they look identical. It'd be like going to the Red Rocks Park in west of Denver. It's a very distinctive looking rocks. But now all of a sudden they're 1,000 miles apart. That's really important. Our final slide that I'll show is the next one, and that is the picture of the topography of the Pacific Ocean floor. You see a lot of things happening there. You see a lot of patterns, and they're going to play a role in all the things that James is going to discuss. So I'll turn it over to you, James, and let's get going. Thank you.
All right, let's switch to the first slide, please. So Antarctica, most people think of it as this giant flat plain that's all ice. Many times you'll see pictures of scientists kind of leaning into snow at high temperatures. And so the assumption is that's Antarctica. Well, it's not true. We're going to through some details that give you ideas about whether there's some real hot spots beneath it, like Walt had talked about. So first of all, if you think about the beginning of Antarctica, like Walt talked about, the continents were all together, and then slowly they started to separate. So when they were together, there were dinosaurs on Antarctica, and slowly as they moved apart, Antarctica became colder. So what we're saying here in general is the Earth is always changing. And so many times when I talk to people, they say, yeah, but that's geological past. We don't have to worry about it. It has nothing to do with climate. I mean, after all, it was millions of years ago. That's not true. And here's the reason. When these continents were all together, they started moving apart. They could see that it was a steady rate. And that's the same steady rate we have now. So here's some of the numbers. Today, entire continents move 1 inch per year. 1 inch per year. So you look back, and if 200 million years ago, when they started separating and they moved 1 inch per year, you would see that it's possible for them to be 1,000, 3,000 miles apart. So that rate of movement, when you use 1 inch per year back then and now, says, look, things aren't that different. And so the changes to climate that you'd expect, dinosaurs, forests, and everything, progressed at about the same rate. So what we're seeing now is not unusual. If there's places where there's a few droughts, then they come back, or forests, and they die. That's part of what happened through time. I'd also up front here, before we get into looking at a few examples of the heat flow beneath Antarctica, where the glaciers are melting, I want to reference a new study by NASA. And senior geologist Jay Zawilli and his team researched this for many years. And what they found is astounding. Antarctica is gaining ice. It is not losing ice. Because a lot of times on the TV programs, you see these melting glaciers and awful pictures. Well, yes, West Antarctica is losing ice, but the whole continent, especially East Antarctica, is gaining ice. So what he said was, this means that Antarctica is actually reducing sea level because the ice is growing in East Antarctica. So that really throws into doubt one of these major points of climate change. Sea level is going to be rising tremendously if Antarctica melts, West Antarctica melts. It's not happening. It's just not happening. So let's move on. We'll start with this slide. Oh, no, go back one slide, sorry. So Antarctica is divided into two pieces like we talked about. There's an East Antarctica, which represents 75% of the area, and there's West Antarctica that represents 25% of it. Antarctica is larger than the lower 48 states. So, as we said, 100% of the melting is in West Antarctica. So why is that? So let's go on to the next slide. Here's one of the reasons. Dr. Eric Stieg from the University of Washington put together with 50 years of data the temperature of the atmosphere just about 6 meters above the ground. And when you average that, this is that map. And it was absolutely shocking to people because there is a warm area that covers all of West Antarctica, the 25%. And East Antarctica looks really normal. And the division between those two is just straight. You would think with global atmospheric warming that the temperature across Antarctica would be uniform. It's not. So why are some of the reasons for that? Let's go to the next slide. It has to do with a giant fault system. We're showing the northern part of this on the north end of the Western Arctic Rift. And so what we're going to do is we're going to go from north to south and go through some examples of where there's tremendous activity and heat flow today, because West Antarctica is actually pulling apart at that same rate, and it allows magma to come up and heat it and melt the ice from below. So here is, let's see, the South Shetland Islands. And an interesting thing about the South Shetland Islands is there's what's it called, a caldera. When a big volcano explodes with force, it knocks the center of it out and spreads out ash all away from it. What it leaves is a lake or a bay. Here in the Deception Island area, it left a bay because there's a little bit of an opening to the ocean. So this is an example of how active it could be in that area. What there is today are smaller volcanoes on the edges of the blown up, and they erupt. And they've been erupting for about 5 or 6 times in the last 10 years. And so they're an example of how things are really still active in this part of the Shetland Islands and northern West Antarctica. Another interesting thing is if you go to another island off to the northeast of that chain, and off the shore of that is a big volcano that sits on the ocean floor. It's called the Orca Seamount. That's volcanoes that sit on the floor. 3 years ago, they were astounded because that volcano started rumbling, and it created 85,000 earthquakes in a matter of a few months. So there's a lot going on up there in the northern portion of the Western Arctic Rift. Off on the right, this is one of my favorite ones, a little bit of a geology joke here, but this is the center of the caldera and the bay, not the center, the side, and it's about 2 miles across. But this is sometimes the first stop for people that come and visit Antarctica because it's nice and warm. They have a ship and close by, and they ferry the people to these hot springs on the edge there. So hot springs in Antarctica, kind of unusual. For the humor for me is that you can see on the left part of the slide, they're rafting people to the shore in a rubber raft. And there's been explosions of this very suddenly. So honestly, I don't think I'd do that. That's kind of a bad news. All right, now let's go to the next slide. We're going to move farther down, farther south. Of course, you can't really say south. There's latitude and longitude but in this area, but we'll call it south along Western Arctic Rift to the central part of it. And we're going to talk a little bit about a giant area of magma that sits just below the crust of the earth. And it's there because a huge magma chamber deep down in the earth. These are about 1,800 miles deep in the earth, these big magma chambers. And when they become pressurized for a lot of things, they come kind of up. The molten lava comes up in a column. And then when it hits the surface, the hard crustal part of the world, it tends to go out and dive back down. So this is a big circulation system. So what happens when, again, in detail, when it gets to the top of the surface, some of it punches through and makes volcanoes, faults that are leaking lava, all sorts of things. That's what's happening in the central part of of the Western Arctic Rift. And you'll note there that there's a little red dot, and it's called the Pine Island Glacier. It's melting very quickly. And it used to be the poster child for all climate change because it was melting so fast and the thickness of the ice was dropping. They said, hey, this has to be some kind of climate phenomenon. Well, it turned out that it's not. The University of Rhode Island did a study on this area, and they were able to see some chemicals coming out of the streams that were melting. And they were able to identify with these mixtures of chemicals that there was an active, mildly erupting volcano under the Pine Island Glacier. So it doesn't really take a rocket science to know if there's an erupting volcano beneath a glacier, that's what's going to be melting it, not climate change. The next one is the Thortes Glacier, and it's been nicknamed the Doomsday Glacier, which I think is kind of dramatic. But the same thing is happening at the Thortes Glacier. They've done research. The University of Edinburgh has done research in them. They found about 100 more volcanoes, and there's still lots of volcanoes in the area underneath the Thortes Glacier. Recently, they have found big caves under the ice sheet, and between the interface between the rock and the glacier, and it's not smooth. There are big caves in there, and they found out that they have some life forms in them. So again, you need heat to form life forms, and that's what's going on. Another article is convinced that there is an active volcano under that. So again, what's going on in Antarctica is not melting of ice due to climate change. Let's go to the next slide. So I won't go into detail here. This again shows the Pine Island Glacier and some faults going through it. Those long areas are faults. And it shows some of the volcanoes there underneath the Pine Island Glacier. Oh, it also shows some volcanoes, the Mount Takagi region. That one hasn't pushed through. But there was a research study that said when it erupted about 2,000 years ago, that it changed the climate of the entire South America, the southern part of the Earth. So that's a very powerful event. On the right, this is just a map of the volcanoes under the Pine Island and the Thortes Glacier, according to the University of Edinburgh. Let's go to the next slide. This is not something that I think people would envision Antarctica being, an erupting volcano. This is on the southern tip of West Antarctica. This is Mount Erebus. It's 12,448 feet high. And you can see there that there's molten lava coming out of it. So this is what's been happening since 1970. This thing has been erupting. So you can even see when you go into space using infrared satellite systems, you can see the red dot of this from space. So it's really dramatic. Off in the distance, you can see another large volcano, and it's lost a lot of its ice. As is here in Mount Erebus, it's lost a lot of its ice. So there are other features of Mount Erebus that are really interesting. If you go down the slopes, there are little fumaroles, I'll say, like in Yellowstone again, geysers. And we don't show one here, but they come out of the flanks of this and squirt out. That shows again that it's very active on the flanks. New Mexico Tech did some geophysics, Walt, in the area of this volcano. And so they could image it deep down in there. And they found that the magma, the molten lava, had moved up to within 4,000 feet of the summit of this. So then on the right slide here shows a bay. Now what it doesn't show there is the flanks of Mount Erebus go into this bay. So if you looked at the left side of the slide, you see the blue is water. Just off that slide, Mount Erebus kind of dives into the ocean. And this area is warmed. And so they've been saying that the glaciers, you can see them here, and ice that's there is again from some type of global warming. Well, I don't think it is. I think what happens is Mount Erebus warms this bay, and it creates these glaciers that are floating out here. If you look down to kind of the lower part, you see some red dot and something that says the Nansen Glacier. This was also kind of a poster child saying that it's going out into the ocean very rapidly, unusually, and it must be climate change. Well, first of all, it's too local. But secondly, it's the warm waters in there. One other fact that helps substantiate that the bay is warmed by geology is there's an excess amount of iron in there in the bay. And Mount Erebus is iron rich, and there's other small volcanoes in areas that are iron rich. So this southern area is very active. I don't have a slide for it, but if you continue to go, I'll say on the right slide, if you continue going to the right, you can vaguely see some areas on land that are kind of colored like rock. This is part of the McMurdo dry valleys. And if we had a big picture, you'd see that extends for 400 miles by 400 miles, and a lot of it is absent of ice. Well, how do you get a whole area absent of ice when the temperature down there is average 14 degrees Fahrenheit, so below freezing? They have contended, the climatologists, that it's some kind of freak wind that comes down here and melts the ice. Well, no. What it is that area is underlain again by some lava from the same type of magma system as under Mount Erebus. And that's what's melting a lot of the McMurdo dry valley ice. All right, let's move on to the next slide. The Arctic Ocean. For many years, people have obviously lived up there in Iceland and Western Europe, and they know that there's some volcanic activity, especially on Iceland. They've accepted it. It's not a big deal. Well, in 2010, Iceland's volcano, I can't speak Iceland, erupted violently, and that's the one on the left. It had a dramatic effect on Western Europe, shut down a lot of airports. There were health problems with animals and people, and it laid layers of ash all the way over to Scotland. So this was a very big eruption. It changed the minds of people, saying that there wasn't much going on in Antarctica. It's stable. This told them there's a lot of geology going on there. On the right is just my favorite slide, showing the initial part of the eruption, sending out black ash on the area. So that's kind of a general setting for the Antarctic Ocean and the Arctic area. So let's go to the next slide. This is the general setting, geological setting of the Arctic Ocean, and then down to Greenland, down to Iceland. And what you see is, of course, in blue is the Arctic Ocean, darker areas are deeper. Then you see these red hashed areas. For instance, on the right side of the slide, you see these red lines, and there are these triangles in between them. These are volcanoes that are present along this rift, kind of like continental drift. That rift there is separating, pushing apart Greenland, and then that part of onshore area to the east. It's pulling it apart. So that area has tremendous amount of heat coming out of it, lava. Now let's switch to Greenland. You can see that there's kind of a thicker area down the center valley of Greenland. And that is another one of these rifts. For many years, they didn't recognize it. Recently, I don't know how many years, they've recognized that that is a rift system. You can see that's kind of parallel to the rift system we just talked about. And so those two are kind of the same active system. Here's an interesting thing. Climatologists, and I don't hold any grudge against them, they're scientists, but they found a 1,000-mile long river beneath Greenland not too long ago. It's a river system. So it goes from the entire south end of Greenland over this weird area of heat flow, see red hatched, and exit in the north side of Greenland. It is such a big river that it's flowing kind of the size as a Mississippi. So how the heck do you do that underneath the glaciers? You certainly can't do it by oceans coming in there because the oceans don't make it here. This valley also slants from the south and goes down to the north. So it's a natural drainage system like you see on Earth. And then it's not just one river. There are streams that come into it, geothermal hot spring lakes under there. So that's an amazing, amazing event. Let's see, what else can I say about that? That's about it there. Oh, I know. Let's talk about the western side of the Arctic Ocean. You can see there that there's this long string, red lines outlining it, and a series of glaciers. To the bottom part of that is volcanoes along Alaska. And then if you go to the north, you can't quite see it, but there's a peninsula in Russia that kind of protrudes out, and that's the northern part of that. So this is a very, very active area, and it heats what's called the Bering Sea, which is the western end there. And in 2014, there was a big change in the habits and migration patterns of a lot of the fish that they get there. This because there was a pulse of heat flow from the rift, went in there, changed the chemistry and the temperature of the water, and naturally the species that live there changed their patterns. Okay, let's go to the next slide. So this, again, the Arctic sea ice in white. And on the right side, you can see this red outline area. That is the rift, the Mid-Atlantic rift that's on the east side of Greenland, like we showed. And then on the far right part of the slide, you can see that's part of the North Pacific Ocean. The Bering Sea isn't currently outlined, but that heat goes into the Bering Sea, then it flows out by currents into the Arctic ice. And so that has acted to melt the western side of the Arctic sea ice, and then the heat from the other rift has melted it. So you'll notice there's something interesting. That melting is very isolated, and it's not melting the ice connection with Russia or the ice connection with Canada. So this is more reinforcement that it can't be global warming that's melting this ice. Now, at times, those barriers aren't there, but long enough that it makes a really good idea that, again, it's not climate change. Let's go on to the next slide. More about Greenland. The 1,000-mile river is there. So if you look on the left side, you can obviously see the outline of Greenland. And what is red is NASA's measurement of heat flow in all of Greenland. You'll notice that there's also some numbers on there in a black line. And if you look closely, you can see the terms, 80 million, 60 million, 40 million. And that is a measurement of when Greenland moved across a mantle plume and went farther this way. And that's what caused the heat to be here. That mantle plume is now under Iceland. They have suggested, scientists, that heat's there is actually just from relic heat. Once Greenland moved over it, it just stayed. To me, that's impossible. You can't have heat like this stay there for 60 million years if there's no eruptions or anything. So I think that path is actually current day heat from a rift that we talked about. And it's interesting that the path of the river actually follows that exact path in there, which reinforces the idea that it's heat flow. Okay, let's go to the next slide. Now we're going to switch to El Niños. This is a fascinating subject. a lot of the climate scientists have said that El Nino forms when the trade winds change or when the currents change, which is interesting. If you listen really closely, they say when El Nino forms, you get changes in the trade winds. When an El Nino forms, you get changes in currents. What they don't say is how El Nino forms. They don't know. They don't know how it forms. Well, my thought is that it's another one of these hot areas. This specific one is over in the western part of the Pacific Ocean. And there, the source point is very small and stable. It doesn't move. And so the heat from that area, the Pacific Ring of Fire area, comes from this 5 little microplates, continents, and they're moving around a lot, and there's a lot of volcanic activity there. And the activity increases for a while. There are bursts of it. And so that creates an El Nino. And you get this El Nino kind of building slowly. And then when it's at full force, you see this cone-shaped temperature of warming. And that cone shape relative to the other areas of the Pacific Ocean, that dividing line is very distinct. It's very distinct. So that's not something you would see with climate changes. So another interesting aspect about El Nino is that it, analog to the upper right, is an erupting volcano, which of course doesn't move. It's a source point. And what it does is it emits ash, and the wind direction from this is from left to right, and it makes this cone shape. So that's a really great analogy to this. On the lower right is a video, and I stopped the video. It's a 3-dimensional video of how El Nino and La Nina, the cold phase, form. And it's not uniform. The forming of an El Nino comes in bursts. And these bursts stay coherent when they move all the way over to South America. It's not an even heating. And that's relative to what volcanoes do. They erupt, and then they burst, and then they burst. So that's another reason it's geological. The last reason that El Ninos are geological, I think, is the one I appreciate the most. It's about helium. Helium has been proven to be a direct indicator of heat from either molten magma that's kind of, lost a little bit of heat, or erupting volcanoes. Volcanoes are known to have a lot of natural helium. And so there's a plume of helium that starts right at that source point and moves out at the same cone-shaped as El Nino. So that's, to me, proof positive. You get a helium plume from volcanic eruptions. Let's see. Maybe while I'm here, I'll mention something else. I didn't generate a slide for it because I only realized it a few months ago. It's about the oceans, ocean temperatures. Ocean temperatures for the last 20 years have been rising, but only a minor amount. They've been, I think, about the last 140 years, per year, the temperature has been rising about 0.02 degrees per Fahrenheit per year. And yes, as you go from year to year, those whole graphs show all those things pretty close together. Well, what just happened 12 months ago is that in the North Atlantic Ocean, the temperature in 12 months changed 2 degrees Fahrenheit. It went from 71 degrees Fahrenheit on the surface to 73 degrees Fahrenheit in 12 months. So that's impossible because you have warming oceans in the global sense, 0.02 degrees. Now you get 2 degrees of warming in one specific area. We've talked about Iceland and Greenland and some of the rifts that are there. Those rifts, I believe, have pulsed a lot of heat. You can see that Iceland is erupting a lot. and that's putting a lot of heat in there. So I think this North Atlantic specific area is warmed by geological features. And the last thing about that is that North Atlantic area, like Walt had talked about, there's a big fault on the center of the ocean basin there. And it's where this lava is rising up, pushing up, and separating the North Atlantic Ocean. That's where a lot of lava comes up. And if there's a pulse of that lava, that's what's heating the North Atlantic. So I'm going to stop for a second and see if anybody has any questions.
Oh, I got some questions about where your red dot is at the origin of the El Nino event. I believe that it will be close to the super volcano Krakatoa.
Yes.
So that is a very active area. And do you think there's enough heat that comes out of that to really cause the El Nino, or does the change of currents cause the heat from El Nino?
I don't think Krakatoa has enough heat. I think it's one specific event, but that area over there, even though it's small, has all sorts of plates tied together. And for certain, there's a lot of magma coming up there. It's along the Pacific Ring of Fire, which, as you know, Walt, is the most active feature on Earth. It has about 80% of all earthquakes happen there. And I think about 75% of all the volcanoes and eruptions. So this area, which is part of the Pacific Ring of Fire, a lot of heat coming out of there. That's what probably fueled Krakatoa, but it also started El Ninos.
Well, a lot of people, I mean, the El Ninos have gone on for a long time, but during the El Nino events, you always hear the news, the hottest day ever, Often that is during an El Nino event, it seems.
Yeah, that's true.
So a lot of these higher temperatures are really caused from El Nino and not from global warming, it seems.
That's correct. The air temperature does increase on the surface area of the oceans there. And of course, when you get that heat, eventually it migrates up into the atmosphere.
I give some geologists credit here in the Denver area. He noticed that whenever we had El Nino events, that the price of natural gas in Chicago would drop. And he published it rather than go out and make a fortune on futures markets, I thought that was pretty honorable, but he's a correct scientist doing that.
Good for him. Let's see, other things about El Nino. I know. Coral bleaching. They talk about the Great Barrier Reef off the coast of Australia. And they say that, oh my gosh, it has been changing recently. It's due to this increased strength of El Ninos, and humans are increasing the strength of those. So there's anthropogenic forces that are increasing them. And so that heat goes over to the Great Barrier Reef, and it kills these corals, large portions of it. Well, there's a couple problems with that. This is a natural cycle. As Charles Darwin stated, it's not the strongest survive. It's actually natural selection. So what happens is when that heat goes into the corals, it kills some things that maybe are old. But what it also did, like forest fires, is it clears the area and it reseeds it for new corals of different species. And so that's what you see in the forest fires in continents, some of them that are going on now. They actually are healthy things. They're needed. And so El Nino is being healthy. It's a natural force. And so geology is doing what it's supposed to. Maybe let's move on to the left.
Do you mind if I ask? I've got a lay person question for you. So I'm representing every person, not geologists or scientists, but just fascinated by the whole thing. I live in Northern California. California is I live on the San Andreas Fault. The San Francisco earthquake took place about 10 miles from where I'm sitting right
Right.
now, over in Olima, California. That was the epicenter. So it might be the most ignorant question that you've been asked, but I'm fascinated. Obviously, earthquakes are a function of plate tectonics. Are volcanoes a function of plate tectonics?
Absolutely. Now I'll speak specifically to California and why there's some volcanoes there and up into Oregon and Washington. What happens there is that rather than the plates moving apart, they're kind of slamming together. And out in the ocean, there's a plate and it dives beneath California. And when that goes down deep, the rocks then melt. And that melting comes up here and causes a lot of volcanoes and earthquakes. It's because you're really moving these plates and shaking them. And that's why there's the San Andreas Fault along that west side of California. And that's why, and then every once in a while, the plates move pretty quickly and you get these giant earthquakes. So that's what's going on in California.
Well, thank you. Thank
Yeah.
you. Sorry to ask such an ignorant question, but the whole thing fascinates me.
That's not an ignorant question. Let's see. Do we have one more slide left? Oh, okay. This is a good one. We can talk a little bit on the left side is the Pacific Ocean, which covers a large portion of Earth, 71%. And you can see the red cone of El Nino and the source point on the right. Now, when the El Nino disappears, you get this cold phase, and that's on the right, and it's called the little girl, La Nina. It originates from the exact same point as El Ninos, and you can even see the patterns north and south of each of those are kind of similar. So they're exactly the same type of event. And you may ask me, well, how do you go for something that's super hot to something that's super cold? This is conjecture on me. I don't know that this is proven. I've never heard it before, so I'm throwing this out here. When the magma chamber under El Nino stops pushing out hot molten lava, you have a transformation to where the fault still stays open. There's no heat, but you can have this cold water going in here. Now, this source area does emit a lot of methane, like you were talking about, methane in these rifts. And so that methane mixes with this cold water and it forms icy ice areas. Excuse me. Ice areas that go in between the cracks, the micro cracks, and the faults above the El Nino area. And it creates these large accumulations of it. And as it creates those, the water is still circulating down to them and coming up. It gets super cool. And that's La Nina. So on the right is a really interesting thing to me. It's a graph through time. I think it goes from 95 to 2010. Hard to read with my old eyes. But you see the graph go up and there's red. That's when there's been a lot of heat emitted from El Ninos. And then if you go to the bottom of that chart, you see a lot of blue. That's when the temperature is very low in the Pacific Ocean. Well, here's something interesting. The amount of energy it takes to go from that red instantaneously over to that blue, you can see right about, well, you can pick any one of them. You see the hot peak and the cold peak. To move from that in a very short time frame can't be accomplished except by geological forces. And so, again, that's kind of a sidelight to what I've been hammering on, is that it has to be geological forces to change things so quickly.
A question, is the area under red about the same as the area under blue?
Say that again, please.
Okay, you see the red areas.
Yeah.
if I was to sum up the area of the red on that
Yes.
chart, would that about be the same as the area under the blue?
Yes, it would
So
be.
we have about equal amounts of heating and cooling at the same time.
We do. Hopefully this gets an answer to your question. So there is a 3-dimensional video out there created by NOAA and some universities that shows the development of El Niños and La Niñas. So it goes deep into the ocean. What we see here are the surface temperatures. But this video shows the temperatures all the way down to the bottom of the ocean. And it's interesting to note that El Nino forms kind of shallow, deep, moves up shallow. At the same time, this video shows that there's cool water circulating under it. So what that says is it's kind of one cycle. And so I haven't worked out all the details of that. Obviously, it's a kind of difficult, but I think it has to do with these gas hydrates, methane hydrates. And so I think I answer your question correctly. There is cool areas underneath El Niños, and there's warm areas under La Niña. Is that good?
Yes, thank you.
So I'm interested. So terribly interested, and I'm a little mind blown. So how is it that the UNIPCC has ignored this, or have they? Can you give us some sense of where plate climatology fits in the larger conversation, if at all, and who's been reaching out to you to work with you or to learn more or to develop this and to understand the role of plate climatology in the larger climate change question?
Okay. No one has been reaching out to me. These podcasts, and thank you so much for being open-minded, is the only way I can communicate some of these ideas. It's really obvious stuff. I mean, it's geology 101. There's volcanoes, they heat things. The second thing is, I don't know why the UN doesn't consider this. They have geologists on there. The United States Geological Survey in the United States also sees all this stuff, and they write and coordinate with the IPC. Why they don't mix in the theory of plate tectonics, I don't know. And one thing that kind of frustrates me, theories. You can put theories out there, and sometimes they don't work. Sometimes they work. But why would you quelch a theory that talks about how geology affects climate? Why wouldn't you just let it out there? And if it's not good, it's not good. In fact, if you start not talking about it and somebody finds it, it ends up really putting a black mark on those people, which is what you're talking about. And what they're doing is they're not following proper scientific methodology. My professors at Northern Illinois University would be turning over in their graves if they saw this happening. What scientific methodology says is, yes, you get a lot of data and you gather it from different disciplines, and then you make a conclusion. You don't make a conclusion ahead of time and force fit the data into it. And I think that's what's happening. So they're not stepping back and taking a breath and including biology, geophysics, all sorts of different disciplines, and considered them. And once they formulated this global climate change theory, they're just stopped. I'm frustrated. It's just
So
completely lost, like you.
the latest information that I saw, and I think it's credible. It seems credible. It tracks with reasonable conclusion from having watched this for quite a while now, is that the global enterprise has spent about $12 trillion on energy transition up to now. 12,000 billion spent already on wind and solar and energy transition writ large. Let's say that's a number. Wouldn't a $100,000 grant to look into this theory, or $1 million spent, let me ask the question: what would a large scale effort take to dig into this, to put together the right team of people and really find out the impact of plate climatology in the larger question of global warming or climate change generally? Because it obviously, as we can see on the screen right now, it's also global cooling, right? La Nina has a cooling effect. So it fits right in the main channel of climate change. And yet you're the only person I know of that I've been able to discover who is pursuing this topic. And I just find it, again, as a layperson, I just don't understand. This seems to explain kind of everything. I see they talk about sea level rise because the poles are melting, but they're not melting because of anything humans are doing.
No. And again, Antarctica is gaining ice, and that actually lowers sea level. So they're not including that.
There's a Mississippi River running underneath Greenland.
Yeah.
And we're not curious about that.
I don't know why. I mean, the research has been out there. And again, I don't mean to be demeaning any group or anything. I want to stick to the geology. But for a moment here, to kind of answer your question, why has this information been ignored? There are some logical reasons. Excuse me. The first one is 71% of Earth is covered by oceans that have an average depth of 14,000 feet. And we really don't know much about the elevation down there in high definition. So what that does is it doesn't allow us to see the little geysers, the volcanoes that are there, how many are there. And there's a project going on right now. It's called the GEBCO project, funded by a lot of institutions. And they have been mapping in high resolution the ocean floors. And what they have found is that there's a lot more features down there than they think. Current estimates are about 1 million. And so they've done about, and there are estimates that vary, but that's the one I've seen the most. So if they've done, I think they've done 29%. So if you multiply that by 3, you could maybe have 3 million features down there. And that really makes sense because Walt showed a picture of the Pacific Ocean. And what that image was, is that it's not just one fault in the Pacific Ocean or around the Pacific Ring of Fire. You can see this is the big fault, and there are secondary faults that come off that one.
Thank you.
So you can see that this one is not even high definition, and look how crowded that is. And so when you look to the right on the coast of California and down to the west coast of South America, you can see kind of this light or darker colored line that progresses northward. And that's where the rift is. And what you can see are these cross line areas. Those are secondary faults that extend out, in some cases, 1,000 miles. So all of these faults potentially have small volcanoes or emitting things from there. So as we become more familiar with these ocean floor areas, it's going to say, look, geology has a lot of force. There's a lot going on here, and we just don't see it. As a follow-up on the polar ice caps, let's say especially Antarctica, It's very difficult to get elevations and readings beneath the, 2.5 miles of ice at the thickness. It's very difficult to get elevations, any volcanoes are there, or eruptions, or lakes that they have found all over Antarctica below the ice. And that's another question. How do you get lakes down there if the temperature of Antarctica is minus 58, minus 57.8? Can't do it. So it has to be down here. But back to this. So it just, I don't understand why people aren't looking at this GEBCO project. It doesn't get their curiosity up. I understand I've been redundant. This is just my
one might suspect that 5% of global GDP over the next 30 years would be a motivating factor to learn a little more. But this question of getting the policy cart way out in front of the science horse, which I heard Judy Kerr say.
Yeah.
Brilliant way to think about it. It does really, again, for lay people, non-geologists like me, I find it profoundly affecting that we want to change. We want to impose energy poverty on a couple of billion people. We're happy with our industrial development, but we think more industrial development for continent of Africa, the southern part of Asia, and lots of other areas of the world is something that shouldn't be done. It doesn't square with human flourishing as far as I could see.
It is. I worked for oil and gas companies for 41 years. And what I found and learned from them is that this energy is necessary. It helps human life exist. And so I'm one of those people that says, look, if you want to change to solar panels and EV cars, let's take some steps. Don't just do it completely. So I've thought about that for a long time. And I guess this is kind of a sidelight I'm getting off to, something that's not geological. I've just written an article about electrical vehicles. And there's a lot of numbers that say it's going to be impossible to meet this net zero by 2050. Part of the problem is, and so net zero is when we emit the same as we capture of carbon dioxide. And they've said, look, we want to achieve that by 2050, especially on internal combustion engines. So there's right now, I think, 300 million combustion engines in the United States. So to convert half of those to electrical by 2050 is insane. It can't happen. One of the problems, too, about the carbon footprint of electrical cars is never considered. They don't have tailpipes, I get that, and they don't emit CO2. But when you look at all the other steps to make an electrical car from beginning to end, which they don't tell you, it has a larger carbon footprint, combustion engines. If we have time, I can go on this a bit. Do you want me to go on or stop?
Well,
we can go on a little bit. Let's go on it.
Okay. Southern Greenland. They're purchased this land, and they're making these plans to drill these big mines that have rare earth minerals that are used for cars, electric cars. The geology down there is interesting. The rocks down there that they're going to mine have significant amounts of natural mercury, and there's a lot of fractures and faults. It also has significant amounts of radioactive uranium. In fact, they were going to open it, and that was going to be the largest radioactive uranium mine in the world. They shut that down, but now they're going to dig down there, and it's going to be safe. Also, there's huge amounts of phosphate in here, and you'll recall that in Florida, there was a big break in a phosphate pond, and it was supposed to ruin this. So, we're maybe this is a bit, I don't know, again, the adjective, but what we're going to do is we're going to environmentally pollute Greenland so we can keep the United States from getting polluted. It doesn't make sense to convert to these electric cars too soon. Okay.
This is Ron Stein's argument, Walt.
Right. He's been arguing that too. We're ruining people. But I think back to your original case you were making is you've brought all these things forward and yet no one looks. And if it doesn't fit the narrative, it gets overlooked.
It does.
And no one is going to fund your ideas for research because it doesn't fit the narrative that they want to find. And that's not really using science to help mankind, really. And yes, I think we got some problems, and I think we're going to have trouble. I think more and more that I find out the cost of going to net zero are higher and higher. We've discussed that on our program. Ken Gregory came up and he said, well, it'll be 200 some trillion dollars. And then we discussed afterwards, well, we're going to need additional copper lines to haul all of this electricity. We need more lines. We're going to have extra costs to take care of the toxic waste from these things. And it goes on and on. And I think it was Dave that was saying it's maybe 400 trillion. And you look at 400 trillion, that's getting up there a lot of money. I mean, it's not impossible.
The whole thing is just crazy. I mean, we should call it what it is. It's we don't have enough money to pay for Social Security. At some point there needs to be a conversation about what our priorities really ought to be.
Absolutely, and I have to give a lot of credit recently to Lord Monckton and Happer, who've been addressing cost versus benefit just recently, and more of that is coming out.
Well, Kim, I think probably, we are up against our natural boundary, but I just want to say, James, I hope that you will continue to pursue this, and I want to encourage everyone to go to climatology.com, which is a treasure of articles and research and things that people can learn more. To visit YouTube and play climatology in YouTube, and you'll get a number of different resources that you can learn there. Find out what you can. This is an important contribution to the conversation. It's been missing, and it shouldn't be. So we're very grateful that you could be with us today and share this information and this important work that you're doing. Very grateful.
Thank you so much for having me.
Thank you.
James, I don't know what to say. I couldn't even come up with a question. This is like so totally new to me, but thank you for your work in this arena and your honest conversation about it. Really appreciate it.
Amen. Thank you.
So, Walt, did you ever dream that this is what would happen with the climate conversation when you started this whole idea about this movie?
Not quite. I didn't know where it would go, but I'm glad it's bringing these things out because we do need to have more discussions on a lot of different things.
Well, absolutely. So, Walt, thank you. James, thank you. And Dave O'Rourke, spokesperson for A Climate Conversation, thank you.
Thank you, James. Walt, great to see you. Kim, as always.
Thank you.
Thank you, everybody.